Hello, dear students. Welcome into the lecture number 4 on atomic absorption spectroscopy. So, today we are going to start the quantification methods of AAS, or you can say working of the atomic absorption spectroscopy. Into that, as we have seen in flame emission spectroscopy, the calibration method, standard addition method, internal standard method, same as that of FES. In this AAS also we can see these that three methods. Okay, so first is the calibration method. Okay, all of you know what is this calibration method. For this method, first of all, a series of standard solution of the element under study is prepared. That means a standard solution, known concentration, standard solution will we have to prepare. Blank, sorry, blank or distilled water is first sprayed into the flame and the readout device is adjusted to read zero absorbance or 100 transmittance. After the preparation of the standard solution, by using distilled water or the blank solution, we have to set our device, that means AS, to read zero absorbance or you can say 100% transmittance. Then the standard solution are then introduced in one by one into the flame in the order of increasing concentration of and their absorbance or percent transmittance value are recorded. That means we have to keep our standard solution one by one into the flame on increasing order or increasing concentration. Okay, then after standard solution, the solution of unknown concentration is then introduced into the flame and its absorbance or percent transmittance is also recorded. That means after the standard solution we have to again keep our unknown sample solution. Okay, and measure its absorbance or percent transmittance. Before each of solution is sprayed into the flame, distilled water is introduced into the flame and the reading is adjusted to zero absorbance or percent transmittance. Okay, before keeping each solution, we have to insert distilled water into the flame to adjust the zero reading that we have already done. A graph of the absorbance value against concentration is plotted to get calibration curve. From this concentration of the unknown solution is determined. Okay, that means we have prepared this series of standard solution, recorded its absorbance or percent transmittance along with the unknown sample solution. We will get the readings, and by using that reading we have to plot the graph absorbance value against the concentration. See that graph. Okay, calibration curve method, this is the graph of the calibration curve method. Okay, on y-axis there is the absorbance and on x-axis there will be the concentration in milligram per dm cube, or you can say in ppm. Okay, so with the help of that standard solution we will get the straight line graph. Okay, because we have prepared a increasing concentration standard solution, so we will get the straight line graph passing through the origin, right? And but one unknown sample solution is remaining. By that solution also we have measured the absorbance, right? But we don't know the concentration, right? So For that purpose, by with the help of that absorbance of the unknown sample solution, when we plot the straight line on this straight line of which is passing through the origin, and from that when we go through the x-axis we will get the concentration. Okay, in this way we can find out the concentration of the unknown sample solution. Okay, this is the actually the calibration curve method. Now we will see the second method, that is the standard addition method. Standard addition method. In this method, the absorbance for the unknown x is first found out by aspirating its solution into the flame with reference to blank. In this standard addition method, first of all, we have to measure absorbance of the unknown sample solution, which is denoted by x. Okay. Then a series of solution having a definite amount of unknown x plus varying amount of standard s are prepared and diluted to the same volume in each case. That means after the unknown sample solution, we have to prepare a series of standard solutions. Okay, that means sorry, a series of x we have to add increasing order as a standard. Yes, suppose first solution is x, then x plus s1, x plus s2, like that we have to prepare the other solution. Their absorbance are then obtained by aspirating them into the flame in the order of increasing concentration with reference to blank. As the unknown sample solution, these above solutions also have to keeping into the AS and measure its absorbance. Okay, then a graph of absorbance A against concentration of X plus concentration of the standard solution gives a linear curve. The concentration of the unknown can be determined from the intersection of the linear curve with concentration axis. Okay, now we'll see the graph of the standard addition method. So this is the graph of the standard addition method. Okay, in this method, this is the x-axis. On that there will be our absorbance. On y there is the concentration term. Okay, in this first of all we have unknown sample solution. We have measured that absorbance of that unknown sample solution, that is x. We will get the particular absorbance, but we don't know the concentration, right? Then we have prepared the certain amount of the x plus a particular standard we have added with increasing order, x plus s, x plus 2s, x plus 3s, x plus 4s, x plus 5s. By this increasing order concentration, we will get the straight line graph. Okay, straight line graph we will get, right? This is straight line graph. After this, when we draw the line up to this axis, and when we extrapolate this line, that will be reaches on this x-axis. Likewise, it will reaches on x-axis. Then we will get the actually the concentration of the unknown sample solution on this x-axis, right? So this is the standard addition method. Now third one, internal standard method. Internal standard method. For this method, a series of standard solution containing same element as that present in the sample solution is prepared. Okay, series of standard solution in this method also prepared. Then a fixed quantity of suitable internal standard is then added to each of the standard solution, blank and sample solution alike. That means a fixed quantity, same quantity. In previous method, we have added varying amount of the standard, but in this case, a fixed quantity of the internal standard will be added into what blank sample solution and our standard solution. In these three solutions, we have to add a suitable internal standard. Each of the above standard solution and sample solution are then aspirated into the flame one by one. That means above all the solution we have to keep into the atomic absorption spectrophotometer one by one. Okay, the absorbance for each of the above standard solution, ASA stands for absorbance of the standard solution, AI that is absorbance of the internal standard, and sample solution A absorbance of the X that is unknown sample solution and its absorbance of the internal standard are then measured at different wavelength on corresponding to lambda element lambda x and other to the internal standard lambda I. That means each of the solution we have to measure a different wavelength. These measurements are made against blank using appropriate hollow cathode lamp or and dual detector. The ratio of absorbance of the standard solution AS to that of internal standard AI, that is AS upon AI, are plotted against the concentration of the standard solution. This gives a straight line from this curve. Concentration of the sample solution CX can be read by finding where the ratio in this case, that is AX upon AI, falls on the concentration scale. Now we will see its graph. See, on this y-axis there is AS upon AI, and on x-axis there is the concentration. Preparing standard solution with increasing concentration, we will get the straight line graph, right? But one more solution is there, that is unknown sample solution. That unknown sample solution, we know only the absorbance with respect to ratio of the AX upon AI, right? By using that value, when we take a perpendicular on this straight line and which is again falls on this concentration axis, we will get the Cx, that is the concentration of the that unknown sample solution. It is actually the same as that of the calibration curve method. Okay, we will get the same the graph like the calibration curve method. So this is the third internal standard method. Now we will see the applications of the atomic absorption spectrophotometer. First application, identification of elements. The use of AAS in this field is limited as for the analysis of each element. A separate lamp is needed. However, with introduction of multi-element lamps, it is possible to detect different element present in sample. Okay. Second, quantitative analysis. A calibration curve is first obtained by measuring the absorbance of a series of standard solution in the required range. The concentration of the unknown can be read from the curve from its measure absorbance. Third one, AAS is used to estimate trace metals in clinical and biological samples. This is the third application. Fourth one, AAS is used to detect toxic metals, copper, nickel, zinc, mercury, etc. in food products. AAS is used to detect traces of metals like molybdenum, tungsten, vanadium, thallium in steel samples. It is used to determine traces of elements in forensic materials, soils, fertilizers, and industrial effluents. It is used to determine calcium, magnesium, sodium, and potassium in blood serum. It is used to determine lead in petrol. Last application is the AAS is an invaluable tool in the study of pollution and adulteration of food, articles, and drugs. Okay, so advantages of atomic absorption spectrophotometry. First one, AAS is highly specific because of atoms of a particular element can only absorb radiation of their own wavelength. Spectral interferences that are frequently observed in flame emission are rarely observed in AAS. AAS is independent of flame temperature. AAS is more sensitive for silver, arsenic, orium, boron, bismuth, cadmium, cobalt, ferrous, etc. Now, disadvantages of atomic absorption spectrophotometer. A separate lamp is required for the analysis of each element. Second one, element like aluminum, thallium, tungsten, vanadium, silicon, etc., which easily from oxides in the flame cannot be estimated successfully. In aqueous solution, the signal is affected by predominant anions. If the two elements present in the sample solution have absorption at the same wavelength, analysis gives errors results. Example, manganese and gallium both absorb at 403.3 nanometer. A like metal like alkali metals like lithium, sodium, potassium have low ionization potentials, hence they get ionized at high temperature. For each element, moderate temperature have to be used to prevent ionization. This weakness of the intensity of absorption and gives incorrect results. Now, they distinguish between atomic absorption spectroscopy and flame photometry. First difference is different hollow cathode lamp are required for different elements, but in flame photometry, flame serves as a source of different element for different element. Second, chopper is used to eliminate radiations emitted from flame. Chopper is not used in flame photometer. So in AAS, the quality of monochromator does not have to be so high to achieve same degree of selectivity because of narrow line emitted by hollow cathode lamp. So in case of flame photometer, the quality of monochromator should be very high degree. AC amplifier is used to amplify only AC current from detector in AAS. So in flame photometer, amplifier is used to increase the output signal of the detector. Fifth difference, the absorption intensity is dependent on the number of larger fraction of unexcited atom, which is less influenced by variation in temperature. The signal is often due to difference of energies between excited and ground state. The signal is obtained from wavelength emitted by atoms. These in this method generally require very high degree of operation skill, but in flame in this method require a high degree of operational skill. It is expensive than flame photometry. It is less expensive than atomic absorption spectrophotometry. Okay, so this is the difference between AAS and flame photometry. So some of other differences also there. Okay, these are actually the instrumental differences. The selectivity and sensitivity differences we have not seen now. So here this atomic absorption spectroscopy chapter will be closed. In the next lecture we are going to start the molecular fluorescence and phosphorescence spectroscopy. Okay, so thank you.